So this video is going to discuss applying a vector field to a standard time plot. So we have here the equation d of x of t, d dt is a derivative function, and we have that the derivative is the cosine of t. Now we know that the actual solution to if we integrate the cosine of t, we end up getting the sine of t. So here in this code, I am creating a time step of 0.01, and I'm going to run my time for 3 times pi. So it's basically going to give me 1.5 cycles of a sine wave. And so I'm then calculating using this t vector. I'm calculating the known actual solution. So we know that if we integrate the cosine of t, we know that we're going to end up with the sine of t plus a constant. I'm assuming the constant factor is just 0 here. But so as I integrate this cosine of t, I get the actual solution to be sine of t. So I'm calculating the actual solution, but then I'm also going to initialize my x and calculate my derivative in a for loop. So for each loop, for every value of t that I have, I'm going to evaluate my derivative. So for each element of the time vector, for each kth element of the time vector, I'm going to evaluate the cosine at that time, which is my derivative showing me how fast I'm changing. And then I'm going to use Euler's method to integrate that. So I'm going to integrate that, and then I'm simply going to plot it. So I'm going to plot the approximate solution is going to be in red, and the actual solution, which I know analytically, we know that the solution is actually sine, so I'm going to plot that in blue. And so I'm going to plot that on a top plot, and then on a subplot then I'm going to plot the derivative to show us how fast the system is changing and what direction it's changing in. So if we look here, at this plot, so we have up here on the top plot, we have x of t is equal to the sine of t. That's the solution. And so I'm plotting the actual plot is in blue, and the Euler approximation is in red. So you can see there the approximation is not quite the actual solution, but it's pretty close. And then I also am plotting the derivative then, dx dt, which was our original given function, which is the cosine of t. So we can see right here at the beginning, the cosine is a 1, it's positive, and it's the highest it gets, which is a maximum of 1. So that gives us the slope of this equation is rising very quickly. Right, so the sine wave is rising in a positive direction very, very quickly. Now when we reach this peak up here, which is actually at pi over 2, right, that is the point that the cosine actually begins to cross 0 and go negative. Right, so we reach the maximum. So when the derivative is 0, we know we're at either a maximum or a minimum, a maximum in this case. And then we start going down. So our sine function starts reducing in value because our cosine is below 0. So as long as our cosine is below 0 here, the sine wave is going down. So it goes down, down, down until it reaches its minimum value, which is at the point that the cosine, which is the derivative, is beginning to cross 0 again and go positive, and then we start increasing again. Right? So this is a simple time plot. So we have time on the independent or x-axis, we have time in seconds, and then we'd have the amplitude of our derivative, and then we have the amplitude of the sine wave. So now what we want to do is we want to apply a vector field. The idea of the vector field is it just simply kind of helps show the direction of the flow of the function. So I've only plotted the vector field for the actual solution of sine of t, as you can see here. But you see the idea is that the arrows are simply kind of helping our eyes see the direction of flow. So we can see that it's, it's going up. It reaches this maximum. It's kind of slow, doesn't go down real fast, but then it starts going down, faster and faster. Then it begins to slow down and turn back around and come up again. So we want to plot this vector field. So really what we need to do is that when we create a vector field, what we need to do is basically pick points all along this whole graph. So when you look at the graph, right, your axes go from 0 to about 9, because remember it's actually going to 3 times pi, so it's going up slightly above 9 is the independent axes, the time axes, and then the amplitude of course is going between -1 to +1. So what we want to do is we want to pick points all along here. As you can see, it's running through here and it's just picking points, and at every point along this plot, just all along here, we're basically building up a matrix, and we're going to evaluate the derivative. So we're evaluating the derivative, we're calculating how fast this is changing. So you see right here that it's going up, it's 2.7 is time, so the time is 2.7 seconds, and then it moves over and it's going up to 3.0 seconds, right? So the amplitudes are increasing as it's moving up at a constant time. And so what we're doing is we're just going along and we're building a matrix that's going to cover this entire plot, and then we're calculating the change. So the arrow that you see there, it's calculating how fast the system is changing. So right now it's changing pretty fast, so it's a pretty big arrow. The arrow's pointing all, fairly well straight down. But right now you notice that the arrow is going almost horizontal, because we've almost reached the point where we're going to start going positive. And then here we're starting to go positive again. So you see it's got a bit of an angle going up. And as it continues on, right, it's going up a little bit faster, so it's going more vertical. And it moves over to the next at 5.7 seconds, it's going even more vertical. And over at 6 seconds, and it's going more vertical. So what we're doing is we're picking all these points within this plot, and we're going to evaluate the derivative at every single one of these points. So we're just evaluating these, and for all these points we're calculating how fast the system x of t is changing, which of course is given by our derivative. Our derivative is telling us how fast it's changing. So down here it's telling us how fast it's changing, and here it's not changing quite so fast, so the angle is getting a little more horizontal. All right, so but for every one of these points here on this graph, we're going to evaluate this derivative and find out how fast it's changing, and that's what we're going to use to draw these arrows. Okay, so we're going to draw, could be 100, could be 1,000 arrows, depending on how many you want. And so we need to create this vector field. Now, that sounds like an awful lot of work. Every single one of these points in here, we have to evaluate the derivative. But using the MATLAB or the Octave tool, it's actually very simple. It's basically about 2 commands that we need to do that. Alright, so if we look at our code again, All right, so we have our original plot, and then what we're going to do is we're going to come down here in this plot, and we're going to use this function called the mesh grid. Now, the first thing I do is I'm getting the length of my vector t, so I know how big that vector t is. It could be, you know, we can use the whos command to see that. If I flip back over to Octave, right, we could see that t is 943 elements, right? So my time vector is 943 elements. And so that's what the length variable is going to contain, is 943. And then I'm going to use this built-in function called the mesh grid. And then making use of the linear space, I'm going to pick points, linear points between the minimum value of t and the maximum value of t. And what I'm doing here is I'm just scaling these by about 20%. So 1.2 is basically, I'm scaling them by about 20% to just kind of encompass everything. And then I'm going to use my axis to kind of trim the plot back once I'm done. But what I'm going to do is I'm going to grab 35 points in the time direction. So 35 points in the time direction, and then I'm just going to choose 10 points. I'm just choosing 10 points in the sine of t and the solution x is equal sine of t solution. All right, and so what this is this is a matrix. This time x is a matrix with 10 values. For every 10 values of x, I'm going to have my time value, which is going to have 35 for every value of t, I'm going to have 35 different values of t. So if we go back and look at this plot here, we have there's basically here 35 values of t, all these blue dots. So there's 35 blue dots in the x direction and 10 in the y direction. Now if you count them, they may not all be showing because I'm then I'm trimming it off to make sure that the graph still goes from -1 to +1 and from 0 to 9.4. So I might be trimming a little bit of those back off. But there's basically, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So it turns out like 8 of them actually made the plot after I trimmed it back down. So, and then I'm not going to go into count in the time direction. But so I'm just picking a lot of points in both the x and the y direction, and for every single one of these points, I'm going to evaluate the derivative. Okay, and so when we do that, here we go. So when we do that, if we look at this time xx, this is a huge matrix where it has 10 elements going down. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 going down. But for those 10 going down, when we look at the y, so if we look back at this plot, there's 10 points along here. Again, only 8 of them actually made the plot after I trimmed it. But there were 10 points that were calculated along here in the vertical direction. So that's what we're looking at. So there's 10 in the vertical, and then there's 35 in the horizontal. And so when we look at the x sine t y, right, you can see, scrolled too far, there it is. You can see it's starting at like -1.18 going up to about 1.2. So when I trim the graph back off, this minimum value and the maximum value of this actually got trimmed off. Okay, but I found that it's a little bit better to expand it and then just use your axis function to trim it back down. When you're done, you just get a nicer plot that way. Alright, and so that's what I'm doing. So I've expanded it. You can see it went to 180, or 1.18, minus 1.18 to about 1.2, and then we trim it back off with the axis commands here at the end. Alright, but this right here, meshgrid, just builds up the matrix of all those dots on that graph. Okay, so when you look at this, all those blue dots, the meshgrid command is just picking those blue dots. And then once we've done that, we use the quiver. Once we pick those points, we get that matrix of blue dots, and then we evaluate the change in time. Now remember that actually the change in time is constant in this because it's just my time step. So this is actually, I've got this scaled. This is actually, I'm plotting this as a 1. Technically here, the change in time is simply the time step. So it's just the time step for every single one of those points. So this here, 1 size, the time matrix is just getting the size of this. So d time is just this huge matrix of 1s. And then dx sine of t is the cosine of the time matrix. So for every element of this huge time matrix, which are all those blue dots on the graph, then I'm going to evaluate the cosine at that time. And so this is kind of a simple vector field here, so it's a simple derivative, it's simply the cosine of time. A lot of times your derivatives are going to be more complicated than that, but it doesn't matter. You have your function of your derivative. That's your system, right? The derivative is effectively the system telling you how fast the system is changing. So whatever that derivative is, you just execute it for every one of your points in this plot, in this huge matrix. You just execute it, and then you call the quiver command. And when in the quiver command, you give it the time XX and the horizontal XX direction. Notice I label these different because these are different than just my straight time up here. This is a matrix of all those dots. So these two values right here are giving the starting point, all those blue dots that are shown on the screen right now. So all the blue dots within here, that's what these two are. They're the X's and the Y's for all those blue dots. And then I'm giving it the change in time. So remember, the change in time is just how fast the time is changing. Now, if you're, in this case, since I'm plotting it versus time and I have a really small time step, I'm multiplying it a little bit. So what I'm doing is I'm scaling it times my maximum time divided by 10. So you may have to scale it a little bit to get the plot to look pretty. And so that's all I did, was I just add a little bit of scaling here because it makes the arrows bigger or smaller. All right, so when you first plot it, it automatically decides the size of the figures based on your derivative in the horizontal direction and your derivative in the vertical direction, and you want those to kind of be consistent. And so I'm actually scaling those. I'm scaling the time one a little bit to just make it consistent with the vertical direction, the dependent axis piece. So this is showing you how fast it's changing in the vertical direction, and this shows you how fast it's changing in the horizontal direction. And so this is what it uses. These, how fast is it changing in each direction, is what it uses to plot the arrows. And like I say, the size of the arrows kind of depends on those, so you can maybe just scale them a little bit just to make them look nice. So these numbers I stuck in here, the TN divided by 10, that was just experimental, so I had to run it a few times till I got the arrows that I wanted and got it what I thought would look nice. Okay, so in this case, again, I started with 35 points in the T direction and 10 points in the horizontal direction, and then I just used the axis command to force the plot back to exactly what it looked like before I ran the quiver. Because what happens when you run the quiver command is it'll tend to resize your axes a little bit to make room for the arrowheads. And so you want to call the axis command and reset your axis back to keep the plot size consistent. Or, you know, it depends. You may just leave it the way it automatically does it, but that's what I'm doing here. So as we see, here's my arrows, and it looks pretty good. Now again, this was 35 by 10. Okay, I also did another one in there which was a little bit larger. It was 45 in the time direction and 25 in the vertical direction. And so let's just, I made a little movie of this to see what this, we'll just kind of run this and see what this looks like here. Okay, so it's just running through and showing us these points, but you can see there that there's a lot more points, so the arrows are naturally smaller. All right, and so I just again, there was like 45 in the X, and what was it, 20, 25 in the Y. I didn't, whatever the name of that file name was, but yeah, 45 and 25. Now again, that, and then I resized them, so it may only have 23 or so in the Y direction, but what that meshgrid does is it picks all these points. So all the points is shown here by the blue dots. That's what that meshgrid command did. It went out, and in that one command, it gave me all these points of these blue dots. All right, and then then I took, and at every one of those points, I took the derivative in versus time in the time direction, or the independent axis, and I took the derivative in the dependent axis, or in the vertical direction. So I took the derivative to find out how fast it's changing in each direction. And of course, in this case, it was a time plot, and I used a constant time step, so the independent axis value never changed. But the vertical one obviously does change, as you can see this running through here. So, and you can see as the arrows, what I'm doing here is I'm just kind of showing each one, plotting one at a time. But in reality, that meshgrid and that quiver command, those two commands in those two steps will give you this entire meshgrid, and with the vector field. Okay, and so you just have to run it a couple of times with some different numbers to just get the arrows the way you like them. So if you want larger arrows or smaller arrows, you can experiment with how many points you pick along this. So again, here I had 45 points by 25 points, and you know, the arrows are a lot smaller. I really don't like this one quite so well because the arrows are so small they're not really readable. So if we went back and looked at the other plot, where that one went, this one here, this was the 35 by 10, and you can just see the arrows are much larger here, and they just show the flow a lot better. Now you could maybe shrink them a little bit, so if I tried, maybe instead of doing 35 by 10, maybe if I changed it to about 40 by 12 or something like that. So when I went all the way up to 25 and 45, that was maybe too much. But so you might need to run it 3 or 4 times and just kind of experiment with the numbers till you get a nice plot. But this is a pretty good plot. I'm pretty happy with this one. You can see the arrows nice. They show you the direction changes as the system is changing, and that's the whole point of the vector field. So the vector field, normally, like, since this is a plot in time, we know that time goes from 0 and moves positive, right? So a lot of times on time plots we don't actually do a vector field, but it does give us a cool plot. It kind of just shows the flow and in there. And so you can do a vector field for any graph, all right, as long as the vector field is showing the derivative or how fast it's changing at every point. So if you have the derivative equation, then you can do that. If not, you can always do it numerically, right? You can take your plot, even if you didn't know what the derivative was, we can do that numerically. We did that the second week of class. And so even there, just by doing that, you could calculate the derivatives, how fast they're changing at those points, and use that in your to build this vector field.